You're going to need properties of limits eventually. Unit 1, Lesson 3 is about properties of limits, and you're going to see that this is actually getting a result, getting a numerical value out of properties of limits is pretty easy, but once we get to derivatives, if we're keeping up with things, doing all the correct work, understanding what we're doing, you're going to need properties of limits. So by the end of this, I hope you can use properties of limits to evaluate complicated limits. And by putting quotation marks there, I'm telling you complicated does not mean actually complicated. It means like technically more complex in this sense. There shouldn't be anything today that looks super crazy. The real thing we're focusing on here is showing appropriate work for substitution. Because if you're not showing the appropriate work for substitution, you're especially on this problem set, you're not thinking about what you're doing. You're just looking at the numbers and taking a super educated guess. So we're going to be doing literal substitution, meaning you are replacing one set of symbols with another set of symbols, and you have to have the exact set of symbols. Now, the cool part, unlike derivatives, integrals, things like that, properties of limits are actually really easy. Everything works like you expect. If you're adding two limits, you can just add the limits, or if you can add the functions, you can add the limits. You'll see what I mean here in a second. And that's true if things are being added, subtracted, multiplied by a constant, divided, raised to a power. Everything kind of works out, so I don't really teach all that much. We just kind of do examples. But like I said, with derivatives, with integrals, with some other things, you do have to pay attention. Not everything all year, not everything in calculus is super straightforward. Okay, so the first thing I'm going to show you, I'm going to say, is barely even a rule. So the limit as x approaches 2 of x cubed. Well, we're not going to do a graphic limit. We're not going to do a numeric limit. We're going to kind of pretend. What you should know is, 2.1, 2.01, 1.9, 1.99. When we cube those numbers, we're going to get numbers closer and closer to whatever 2 cubed is. So we're just going to call this 8. Do I have this animated? I do. Okay, so I don't have to do that. Cool. Likewise, as we choose numbers closer and closer to 2, 1.9, 1.99, 1.999, well, x turns into numbers closer and closer to 2. That's easy. And even easier is the limit as x approaches 2 of a constant. When we put in 1.9, we get 1. 1.99, we get 1. 1.999, we get 1. Okay. So what do you suppose we would get for the limit as x approaches 2 of the sum of x cubed plus x plus 1? And the answer is, of course, 8 plus 2 plus 1. Each of those individual limits up top added together. So you might not think of that as a big deal, but it kind of is. What this says is the limit of a sum of functions, that's down here, right? We added the functions together into the limit, is the same as the sum of the limits of those functions. And that's not just, well, number one, I don't think it's wordplay, but whatever. That's not just clever wordplay. That actually tells you the difference. So if you need to add up a whole bunch of limits, you could also instead just add up the functions and then do the limit at the end. You'll get that. So why would that be the case? Well, let's think of this graphically. The limit as x approaches 2 of x cubed is 8. And let's think of that as this vertical bar, 8 units high. And you can see over here, I've done the same thing. I've transferred that over. I've given you a graph of x cubed plus x plus 1. The limit as x approaches 2 of x. Can I get it blue? Maybe. This is so much easier on a touch screen in the front of class, right? This height of 2 is stacked on the height of 8. and then this green height of 1, oh, there it is. This green height of 1 is stacked onto the top. So hopefully that's a nice visual. Let's see if this opens the first time. Okay, cool. And so we better turn these all on. Okay, so there are the three functions, and here's my f plus g plus h. Let's turn f plus g plus h off. So as I move left and right, this bar follows the height, and we can think of the height of this bar as the limit as x approaches whatever my c is here, 1.9, of just f. Kind of hard to see just because of the way I've programmed this, but as I move left and right, the height of the blue bar up here matches the height from the x-axis to the blue part. And so hopefully you get the idea that, well, that's one everywhere for the green part. As I move left and right, those three functions, x cubed, x, and 1, their heights are all stacked together. So I might as well just do the limit of the composite function f plus g plus h, or x cubed plus x plus 1. Maybe I should attach that for you to play with. Come on, how do I switch back? There we go. Okay, so I already said this to you. This left-hand side is the sum of the limits of functions. We're adding up three different limits, and the right-hand side, how did we say that? Is equal to the limit of the sum of the functions. So showing what you know is something I'm going to be saying a lot, especially if you're in my class, but this thing is all about proper notation. So you could be given stuff like this: the limit as x approaches 2 of g is 4, and the limit as x approaches 2 of h is 3. Now a lot of people just say, hey, this is clearly 2. And they're right, but the reason I think they say 2, I've done this a long time, is they're actually not looking at the limit. I think people are looking at, well, g is equal to 4, so the square root of g is equal to 2. And I suppose that's a way to kind of get the correct result, but it's not really what you're supposed to be thinking. So we don't know what g is. G might look like a sine curve. G might be exponential. All we know is if we put numbers near 2 into g, we get y values closer and closer to 4. So what you're supposed to know is that the limit of the square root of a function is the same as the square root of the limit of that function. And this is the making an exact substitution. So in red, we do not have this exact same set of symbols. We're really close. We need to get rid of that square root. And the limit of the square root of a function is the same as the square root of a limit of that function. So we can just kind of pull that square root out, for lack of a better word. Phrase. And now we do have the exact same thing. Limit as x approaches 2 of g, no more, no less. And now we can replace limit as x approaches 2 of g with this 4, and now we get 2. So try to think of your answer as the proof about what you're allowed to do, right? 2 isn't the answer. The rearranging is the answer. That's the content you're supposed to know. So that's what I'm saying here. Whenever I give this assignment, I always have to give it back every year because a whole bunch of people will do kind of originally, they'll just write this, and maybe they're thinking the correct thing, maybe they're not. Most likely they're not, and so they have to redo it. So here we go. And this is exactly what we said. The limit of the square root of a function, that's what we started with, is the square root of the limit of that function. Oop, we lost our 2. Okay, so same setups. Limit as x approaches 2 of g is 4, and limit as x approaches 2 of h is 3. And so again, people just see this and they're like, 7. And maybe, but again, did you actually rearrange and show what you know? Probably not. You just saw a g here, and a 4, and an h, and a 3. But what you're supposed to know is, well, the limit of a sum of functions, ooh, I guess I have to do it out. I thought I had this typed. The limit of a sum of functions is the same thing as the sum of the limits of those functions, meaning instead of doing the limit of these two functions added together, each one gets their own limit as x approaches 2. And now I do have limit as x approaches 2 of g, which I can replace with 4, and the limit as x approaches 2 of h, which I can replace with 3. That's what we're looking for. What's your answer? Your answer is all of this proof. Okay, so hopefully you're getting the idea. It should be pretty straightforward now. Again, hopefully you're understanding what I meant at the beginning, that, well, the rules work like you think they should. The limit as x approaches 2 of g times h is going to be the same as the limit as x approaches 2 of g times the limit as x approaches 2 of h. And now once we have, these exact same sets of symbols, we can replace limit as x approaches 2 of g with 4, limit as x approaches 2 of h with 3, and actually get what we're supposed to. But I do have that written out. Yeah. Okay. All right. So how are we going to break this apart? The limit as x approaches 2 of 2g plus 1. So limit as x approaches 2. We know we're going to be using this 4, so we want limit as x approaches 2 of g of x. That's how we're going to get a 4. And then, well, what happens to that 2? Well, I guess we'll just put it out front. That's our constant multiplier, so that's going to be end up 2 times 4. And there are two ways to write this one. You could just write 1. But what would be better is to make sure you know, well, the limit as x approaches 2 of 1. That means, you put in 1.9 and get 1, put in 1.99 and get 1. So I think it's probably best to write out limit as x approaches 2 of 1 and then add 1, so it's clear that you understand actually that limit applies to everything. Alright, hopefully we're getting the hang of this. Limit as x approaches 2 of h over 3g. We're going to rewrite limit as x approaches 2 of h over 3 times the limit as x approaches 2 of g, which means we can write 3 over 3 times 4, and I suppose you could simplify, but that's not really a big deal. All right. So evaluate each of the following. Man, there's a lot going on here. This is actually from our textbook. So the limit as x approaches 3 of 2f plus g. Okay, maybe I think I'm going to do this in color. So this it doesn't pick it. My brain doesn't pick this out. Here's f. Oh, can't get black, huh? And then red is g of x, and then black will just be h of x. Okay, I can handle that. Okay, so here, I guess I have to write tiny. We're going to do 2 times the limit as x approaches 3 of f of x plus the limit as x approaches 3 of g of x. And limit as x approaches 3 of f of x, well, that's 0, times 2 is 0, plus the limit as x approaches 3 of g of x. Man, I have a lot of writing to do with not enough room. So the limit as x approaches 3 of g of x does not exist because the limit as x approaches 3 from the left of g of x is 6, and the limit as x approaches 3 from the right of g of x is 4. Since those aren't equal, hey, we can't do this. So maybe I will erase all of this and write 3 from the left. Oh, it was g of x, wasn't it? Limit as x approaches 3 from the right of g of x. And let's see, 6 does not equal 4. So how can I do as little writing as possible? Maybe up here I'll squeeze in does not exist. Right? Because if that limit doesn't exist, I should probably be writing more. But if that limit does not exist, then this more complicated composite limit does not exist. I think this one we can do. Cool. So the limit as x approaches 3 from the left of g. Yeah, the one-sided thing is going to work. I decided instead of struggling to fit everything, I would just kind of pause and rearrange. Okay. So let's get rid of that stuff that I had previously. Okay, so what we're supposed to write here, how we need to rearrange. Limit as x approaches 3 from the left of g of x, separate from the limit as x approaches 3 from the left of h of x. Oh, h of x is the black one. I'm going to start with that because I'm going to forget. Okay. Limit as x approaches 3 from the left of h is just -2. And the limit as x approaches 3 from the left of g, that is 6 from up top. Okay. Right now, chronologically, we're doing derivatives. So when I look at f over h, I'm thinking quotient rule, but limits work out nicely, so you don't really have to do much. We can break this apart as the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of h of x. Limit as x approaches 3 of f is 0. I don't really like equals, but I'm out of room here. And the limit as x approaches 3 of h is -2. So we just get 0 overall. And hopefully you can figure out how to do that last one. I'm out of room and I need to go to work.